a administrative thing. If you haven't already done so, please sign the sign-in sheet at the end of the talk so that we can keep track of attendance and things like that. But today it's a great pleasure to introduce Professor Jorge Nocedal, the Walter P. Murphy Professor of Industrial Engineering, Management Sciences, and Applied Mathematics at Northwestern University. Jorge is an expert in all things optimization and has won many awards, including recently the John von Neumann Award from SIAM. And we're really excited to have you talk.
All right, thank you very much for the organizers, everybody here, Applied Math friends. I have a courtesy appointment in Applied Math department. And sometimes when people ask me, what are you? I never say industrial engineer. And there's a great department at Northwestern. I'm something between a computer scientist and applied mathematician. But these days, who knows, right? Stats, machine learning, and all those things. Great. So this talk is going to be about training, just training deep neural networks or any of the networks that we have today. Nothing about neuroscience, just cold machine learning. How do you train them? Well, you train them with what's called backpropagation. They use that word, backpropagation. But backpropagation means computation of derivatives and then the application of a gradient descent method in order to find the optimal weights. Now, it turns out that that optimization process is not well understood. It's exceedingly expensive to train one of the modern neural networks. It takes weeks to train a neural network on whole farm of GPUs. And the training and the inference of machine learning systems now is consuming as much energy as mid-sized countries, as Argentina. You've probably seen that the usage of AI right now is comparable to the whole usage in Argentina. And where does it come from? Inference, whenever you go to ChatGPT and you're asking all these silly questions, there, and when you train, right? So it's imperative, actually, to improve the optimization process for environmental reasons, economical reasons, but especially to open up the field for people who don't have enormous computational resources. It's very important, for instance, that now that large language models are there, that the public doesn't only do fine-tuning, but maybe they have a chance to do pre-training. And I think there's this community in optimization that says, can we reduce memory costs, CPU time, in order to make things like this possible, right? All right, so.
The query versus the training, is this like orders of magnitude difference?
Oh, yeah, okay. So the question is the computational cost of the query of inference compared to the training. What are they? And I don't know the right numbers. But I just know that the training itself consumes a huge amount of time. And queries, inference is done with lower precision. People are pushing to the lowest precision for floating point 8. And you probably, it's very difficult to go below that. It's actually surprising that you go to below 8. And thank you for asking the question, because I think I have a lot of material here that is not relevant, is too deep into optimization, and maybe want to stay more in the a high level here. So the question is, optimization of training neural networks is not well understood, because if you think about it, why does it even work? And when people write papers, there is a lot of confusion. People keep reporting conflicting observations. People find results, they gloss over them, and they go on to the next thing. Some aspects are well understood, and I'll talk about them. But what we know is that empirically, you can train a neural network. We know it's possible, right? Now, the advances in machine learning in the last 15 years have been made possible by a combination of two things. Innovative architectures, and I'm going to talk a little bit about this, architectures that are conducive to be trained. And second, development of optimization algorithms that will work for the training process. The interplay with these two activities is the key. And I will not talk here a lot about the theory. There's an immense amount of theory about a two-layer neural network and all sorts of properties like that. I'm going to be focusing more on the computational aspects of training a neural network, meaning I have students and colleagues in the tech industry and have discussions with them. By the way, a student who graduated 2 years ago, Michael Shi, he graduated from our department. This year, he and his team at Meta won the machine learning training competition, which is called the ML Commons. It's a competition set up by Google, Meta, and other companies. They create some benchmarks, ask people to produce their code, and they run it, and then they see quality of results and speed. And I was glad to see that my former student won by a lot, and they beat what is called the Atom method. I will talk about it in a moment with a more advanced algorithm. And so now there's a little bit of a excitement about maybe things are going to be changing there. So we want to talk to that community, to the industry. Some open questions. How can we design neural network architectures that are conducive to optimization? And the use of skip connections, residual networks, normalization layers have made a huge change. And I'll describe that a little bit. The other thing we want to understand, what is the landscape, optimization landscape? How does the objective function look like? What is the intrinsic dimensionality of the problem? You hear that people say that large language models use billions of parameters. Do you need billions of parameters? When you actually optimize it, what is the space that the optimization algorithms explore compared to these billions of variables? And can we design more powerful optimization algorithms that balance nonlinearity and noise? This is a field where theory has followed experimentation all the time. So if people, for instance, come up with residual networks, and then there are a lot of papers trying to explain why they work well, and so on. There are probably at least 1,000 papers that are devoted not to the theory, just to the computational aspects of machine learning. And it's a rapidly evolving field. Everybody's very excited about transformers these days. And as Becca and I heard in an impressive plenary talk a couple of years ago from someone who's really inside the industry, large language models are doing things that people didn't expect them to do. It is surprising, so we are in an exciting time, right? Now, optimization plays actually a dual role in machine learning. So first of all, it finds the parameters. It's used in training, right? So it determines the parameters, the weights of the neural network. And once you have the weights, you put the information here, boom, and you got your prediction. All right, so we know that. But what is not so well known is that when people are designing architectures, when someone is designing a new architecture, if they cannot train it, they abandon the architecture. So if for some reason we haven't delivered enough optimization algorithms, or if that person was not persistent enough or clever enough to use optimization properly, that idea gets just shelved because you cannot train it. And we believe that there's a cycle that has happened. There's an optimizer called Atom that everybody's using. And so the perception is that if you come up with an idea that cannot be trained with Atom, then it gets rejected, right? And so optimization plays that dual role. And that is why the industry actually is quite interested in the, there are many machine learning experts who learn about optimization. They teach each other, they read books, they go to lectures, and that's one of the rapidly increasing fields of optimization. All right, why has deep learning been so effective? Why are these structures so effective? Well, it's a special kind of function in neural network. We know that it has high expressive power. The other thing is that from day one, they were designed to be fully differentiable. So, well, there may be ReLU there, but it doesn't matter, right? Work in the space of real numbers. Don't work in the space of integers. Even though neurons may be 0, 1, we have to work in the space of real numbers because we're going to have to do high dimensional and high dimensional optimization. Cannot really be done in a mixed domain. Make it fully differentiable and then make it optimizable. And this was a complete fluke. The people who invented these architectures, they did not know that they were going to be that could be optimized. The key always is activations have to be nonlinear. The activation function has to be nonlinear. I don't know that it's possible to do an intelligent function of this kind that doesn't have a nonlinear activation. And here you see the more typical ones used in industry. And the objective function that you minimize is what they call cross-entropy laws, which is sort of generalization as a maximum likelihood estimation. You just try to guess the data that you have as well as possible. All right, so if you create a huge neural network like this with millions of parameters and you train it, can you really find a set of weights that's going to work for all the data that you're going to be giving it? Right, so you train your facial recognition phone, and now you're going to get lots and lots of different data of different people. Is a set of weights really going to work for all of that? Well, the objective function is highly nonlinear, and there are so many weights. Does the function that you minimize look like this, or does it look like that? So if the objective function that you're minimizing looks like this, and you start at the right place, you're probably going to get to the right. But if it looks like this, who knows where you're going to get? And what do I have here? I have a picture of actual loss functions of deep residual networks, and these are slices in 2 dimensions. These are actual pictures, and the nice neural network on the left has these residual blocks that I will explain. The other ones do not have them. And in fact, training neural networks was becoming impossible at some point. Now, I find it, yes, good.
Big enough that you would just have tons of close to global minimizers. But I don't know.
So the question is, do you think that these pictures are representatives? You have in mind problems where they have many minimizers. The objective function is many minimizers. I am very confused about the picture in my mind because I always have one picture that I know is wrong. And my picture is all neural networks that I know, even transformers, are degenerate. The minimizers are degenerate. Means that at the minimizer, they're in invariant directions where the function is flat. Why is that flat? Well, when systems are overcapacitated, it's because of that, right? But the neural network itself, by its nature, if you have an arc and node and another arc, if you multiply by 1 by alpha and multiply the other one by 1 over alpha, you get the same result. So they're invariances. So the picture that I have is like a Mexican hat, that there are minimizers and there are families of minimizers like this. And whenever we do experiments, it works like that. Whenever we do pictures, it never looks. What happens is now this is too high dimensional to be seen, right? So are these pictures just fooling you or not? Well, the only thing I can say is that these are pictures from the person who invented residual networks, uses these pictures in part to motivate what he did. But I'm going to talk more about that. He's got a much better explanation of what it is. I'm always worried about pictures of optimization in 2 dimensions. It's always the same thing. You get the contours like that, and everybody starts saying, oh, I know how to do better algorithm. You take this, this, and that, and I'll put another line, and this is Nesterov's algorithm, and that's not true. Nesterov's algorithm is a mathematical miracle, right? Some coefficients that work just precisely right, not pictures, right? So good thing. At the very beginning of the field, one of the first people who worked on neural network was Rosenblatt in the 1960s. He was not the very first one, but he had a machine, and they were making big statements about everything is going to transform the world. This is the first, he said, I'm creating the first system that is shaped by data. He was already talking about the right way of seeing things. And one of the leaders in that field, Marvin Minsky, kept writing on papers things like this. I don't believe this is going to work. Because even if a gradient can be computed of that objective function, unless the structure of the search space is special, which I don't know what it means mathematically, the structure of a space is special, hill climbing will do more harm than good. So I think what he meant is, unless the objective function has some very benign properties, I think that trying to minimize is going to be like playing the lottery, right? Now, that's 1988 that he was saying that. We know now that the landscape is benign. It has to be benign, otherwise things wouldn't work. And we have much other evidence. But we don't really understand why and what way it is benign. And there is a concern that we are creating systems that are used in everyday life that lack theory. Theory is following heuristics, as I mentioned, and it's highly incomplete. So we're dealing with a purely experimental, heuristical stage of computer science. And even computer science that you would say, well, it's not mathematically inclined. Everything that people did in computer science over the last 100 years was understood. I mean, when people had better database, people had better searching, whatever, risk architecture, it was understood, right? Now it's not understood. Now it's empirical, we're going this way. And one thing that I keep in mind, when Becca was saying, what picture do you have about the neural networks? I don't have a picture, but my picture of the field is the following. When Columbus was talking to the monarchs of Spain about doing his trip, I read that one of his advisors, or more of them, told him, you know, this guy is totally underestimating the size of the world. He's planning for a trip that's not going to work. He doesn't have enough things. This is way too big. Don't fund that. And for some reason, they funded it, right? Now, we don't know what in between here is, like neural networks. Just do it and see what happens, right? If the guy dies, no problem. He's a big talker, right? So let him go, right? And then in 1942, he discovered something, and he made 4 trips. And after 4 trips, he didn't understand better what he was still thinking he got to the Indies. So I think we're a little bit like this, that we've discovered something, we know it's big. As time goes by, it looks bigger. We're not exactly sure what it is. We don't know what the limits are. But we have to accept it because sometimes things work that way. So Columbus was lucky because there happened to be a continent in between. Otherwise, it would have been trouble here. And here with neural networks, we're lucky because for some reason, the stuff is working. And in particular, the question about the expressivity of the neural networks, attention mechanisms, and the optimization process, that all these things are working, is luck, because it's not like we discovered that. All right, just to get a little bit of perspective of how the field evolved. Machine learning has been around for a long time. Neural networks have been around for a long time. They had successes and failures over the years. But in around 2011, they did a series of experiments. The group around Jeff Hinton did some experiments on speech and image processing that really changed the field. So there's something called AlexNet, considered to be the beginning of the new era of neural networks, machine learning, used only 8 layers. So deep learning was 8 layers and 60 million parameters. But already at that time, they were using data augmentation, ReLU activations, and GPUs. Now, it turns out that if you take today, if I give you the AlexNet, which is easily obtainable, you will not have any problems with training it. Training it will be easy. But that was 2011. As people started making the networks deeper and deeper, it became increasingly more difficult to train. And by 2014, people were reporting that when they were trying to do the optimization, they're encountering vanishing or exploding gradients. That sounds very spectacular, right? What does that mean mathematically? Slow convergence and the necessity of using very small step lengths like that. And techniques that were done in order to try to improve things were insufficient. Exploding gradients means the gradients are becoming very, very large. Vanishing gradients, some weights have no effect anymore. You've done a neural network, for instance, a recurrent neural network so convoluted that when you find out what's the partial derivative of the objective function with respect to that cost, is almost nothing. And you have lots of those. But other gradients are very large, and you don't believe that it's true, that just some parameters are going to determine everything. It's a concoction of the architecture. You got yourself, painted yourself into a corner. So deeper and deeper architectures were becoming difficult. But around 2015 and 16, people came with two big ideas that changed things. One is called batch normalization, which I'll try to explain, or layer normalization. It was designed in order to improve the optimization, but people found out that it also improves generalization. And then there is the idea of residual connections that made the deep learning possible. Now, these are the algorithms that are being used in practice, but I will not talk much about this. Now, just to have a general idea, a mathematical or approximation theory or learning theory perspective of what we're doing here is we're trying to create a prediction function. And we want it to be good. We want the expected value of the error in making predictions to be small. But that error has three components. The first one is the approximation error. We have a neural network of a certain size that can only represent certain things in the space of all things that can be said or images that exist. We have an approximation error h. We're living in that function h of the neural network that we're working on. Then there is an estimation error. We're not minimizing over the entire population. We're minimizing the objective function with respect to the training set that we have. And finally, you optimize your objective function to a certain degree. And all of these things have to balance each other. There is no point in doing optimization to a much higher degree than the estimation error would be. And so you have to see where actually are the problems here. What is causing you more difficulties? Of course, the approximation error is a more difficult thing for us to try to even contemplate what it means. It's very surprising that for images, image classification, errors are almost zero, which means that the approximation error is not very large, right? But now we got into language, and more than that, predicting the next word, the next sentence. Well, there are errors, they're big errors. We don't know what that is. To what degree do you train the neural networks, right? And right now, how much you optimize is something that is determined by time more than by I have converged to the solution. I want to just say a question here about the practitioners, because there are so many people, just in my family, cousins, nephews, so on, are talking about, oh, I'm using the learning rate, I'm using LoRa, I'm using fine. They're all, they're all into data science, right? And the learning rate, the step length of the algorithm, right? So you have an optimization algorithm, and you have to decide how big the step should be. It turns out, and I will not get into really what the math here is, but if you look at the expected value, expected improvement during the optimization process, you have weights, k plus 1, and you have an estimate of the weights k, and you're updating them. How much progress do you make in decreasing your loss function depends on a negative quantity. This is good, you're making progress, you're decreasing your true objective, and there is a positive term. So there's something that is driving the optimization down, and something else is creating problem. And this second term really is noise. This second moment is really noise. But when you do the analysis, it turns out that the first term depends linearly on the step length, and the second quadratically on the step length, which means that if you make the step small enough, you can compensate for noise. You can decrease noise so you can make progress. And so in machine learning, they call it the learning rate, which is also not informative. But what you really try to do is balance nonlinearity, how far can I move, with controlling noise. And this is something that people are trying to do with just one algorithm, like one algorithm is going to do the two things. And that seems pretty impossible to do. That's why there's this learning rate. People are playing with the learning rate. And a typical machine learning system, when it's trained, is trained with maybe 100 different choices for that alpha. And then you find out which one will work, and then you use that. Now, do all optimization methods yield the same generalization? When you apply an optimization methods to a training neural network, do you always get same generalizations? Well, here's an example that we produced in 2017, and it's still valid today to some extent. Suppose you have an objective function that has two minimizers at the same level, but one of them is a wide minimizer and the other one is a sharp minimizer. And this is the minimizer of the training function, right? You have data, and with that, you're trying to minimize your, you're doing a regression, right? Which of these two minimizers would you prefer? Well, in an optimization, we call them robust. The wide minimizer is robust, and the other one is a sharp minimizer. Well, it is known now, after many years in the area of machine learning, is that if you can encourage your optimization algorithms to go to flat minimizers, you are in fact going to get better generalization. What happens with these minimizers, that's subject to discussion, right? Can you somehow guide the optimization process towards those minimizers? And that people would call that implicit regularization, right? You make things more robust. Instead of putting an explicit regularizer, if the optimization algorithm can navigate to those regions, it's going to work better. Now, in general, the field of robust optimization tells you, oh, we're not interested in just getting to the lowest point of the function. But I want to know is, I have a disk, where can I put the disk down as much as possible, right? So you minimize the maximum value that that function has in a neighborhood. Where is the maximum value the function is the least, right? This is robust optimization. And we would like to do robust optimization in neural networks, but formally, correct robust optimization is too expensive. You use semi-definite programming or conic programming, you cannot do that. And this is an experimental science. People are trying to play with ideas that emulate this. For instance, you will find among the 1,000 papers that I mentioned something called sharpness-aware optimization method that has something that I will not describe in much detail and says, oh, here's a heuristic, and this is going to tend to guide you to the appropriate minimizers. And there's some truth to that. So here's an example of a residual network. And here are slices of minimizers obtained by the stochastic gradient method, and this is by the sharpness-aware minimizer. And they try to plot the objective function around here, and they see that if you don't do anything, you come to the regions where the minimizers don't look wide, but that algorithm that tries to promote robustness does that, right? Now, do people use that algorithm in practice? No, because it's more expensive. And why? Because by playing with other things, maybe you can get to those right minimizers. Also, by the way, it's not a right solution. It's a empirical solution. But people give information to try to back up statements like training a neural network is an optimization problem that is underdetermined and needs to be regularized. Can we do some sort of implicit regularization? Can we make the algorithm go to the right type of minimizers, right? The minimum norm minimizers or so. So let me talk a little bit about architectures from the point of view of optimization. I mentioned batch normalization and residual connections. Whenever you do nonlinear optimization, what is the key thing, the starting point? Where do you start, right? And here we are in the world of applied mathematicians. There are tons of problems that are solved that are based on differential equations, for instance, design problems, control problems, and so on. Where do you start? Well, you start with a design that is very close to what you wanted, as close as what you like. But for deep neural networks, the initial point is the initial set of weights. What are the initial set of weights? What idea? Do you have any idea what they are? And so people say, no, we don't. We're going to choose them at random with some considerations. So the considerations are the following. If you consider that the information you're giving to the neural network here is random in some sense. It's pushing random data. If you produce random weights, it's going to make the result more random, right? So we look at the variances, and what we get is the initial variance of the data gets multiplied by the variance of the weights, and n, which is the number times n, which is the number of neurons. And what you want to really control is the variance. How do I make this term as small as possible? Because this one is fixed. So there's a very simple rule. You make the variance to be 2 over n. Or the standard deviation is square root of 2 over n. And very simplistic reasoning. So this is used in practice. How do you start the weights in the optimization process? You choose them from a normal distribution with mean zero and standard deviation 2 over n, where n is the number of neurons of the first layer. Now, you would like to do this analysis for all the layers, but we can't. We can't do analysis of almost anything in deep neural network because it gets too nonlinear, right? By the way, this dot product activation, it's at best a polynomial. If you have 100 variables, a polynomial of 100 variables, and if you have 20 layers of degree 20, and we don't know what that is, right? And people use models from a spin glass model and so on to try to find out how many stationary points are there and minimizes and so on. And if you go that way, it looks like the problem is hopeless. You take polynomials of high degree, there are minimizes and stationary points everywhere. So in any case, another heuristic, you should choose a starting point that way. And layer normalization is an idea that I think it's become so important. Without that, I don't know of any system that does not use what is called layer normalization or batch normalization. Now, each neuron can take arbitrary values, right? We don't know what these neurons are going to do during the course of the optimization. Why not create some order among the neurons so that maybe neurons that are together are doing something similar and other neurons that are similar do something similar? Let's try to put some order between them. So how about if you adjust each batch? You're going to take the neurons and take a group of them. You're going to call them a batch, and you're going to renormalize when you're training and you're getting values for those neurons. You're going to normalize them. You're going to bring them together. In particular, what you're going to do is these are now the group of neurons. So suppose that C1 represents 50 neurons. What you're going to do is, among that 50 neurons, you're going to take the mean of them in the standard deviation, and you're going to subtract that to them. And that's called batch normalization. And you do that for every one of them. So you don't let the neurons fire completely arbitrarily, but you put that order, also derived heuristically. And it facilitates the optimization process enormously. But the one thing I wanted to have time to talk about are residual networks. Yes. Oh. Yeah, and she was saying, and are these orders maintained during the optimization process, or are they shuffled along, right? I am much more familiar with a setup where they're fixed ahead of time. By the way, since you asked that question, you've probably been hearing about fine-tuning large language models. You have a pre-trained neural network, which is enormous with billions of parameters. Then you get one of these systems like Llama, which is an open source system. And it says, you create new data, and there's this software that is going to adjust the neural network so it is good for latex. I don't know, something. It's going to be better at latex. You give it a lot of examples, right? And the fine-tuning works in a subspace. Instead of moving those billions of parameters, only move some of them. And the first successful idea was to only update the attention, the parameters of the attention matrices. But recently, people have found that if you go and change these coefficients in batch normalization during fine-tuning, it also helps. Instead of taking those numbers, you learn the numbers in batch normalization.
Talking about the energy cost, and you said one thing people will do is they'll like quantize the weights for inference. So I guess I wonder, like, does batch normalization then affect how accurate a quantized network is? Like, is there some interplay there?
I'm sure there is, but to understand it, and when you say quantized, mean just lower precision, right? Right. 8 bits, yeah. I'm sure it does. But how does it do it? I'm sure it's very difficult to understand, right? Because one is a training process that goes over a lot of data. And by the way, you're doing regression, right? Over the data. How many times you go over the data? Before large language models, people would have a lot of images, and they would go over the data 20, 80 times, like that. So many, many optimization iterations. Large language models have billions of parameters and billions of training points. What is the balance, right? Well, the secret of some company that I will not mention is to do maybe 2 passes over the data. Now it's a little bit easier to say that the training, you can see the effects of the training, right? 2 or maybe even 4. Oh yeah, so I want to talk about residual connections. Maybe the last thing I want to talk about, and then just take questions. So good initialization and layer normalization were not enough to train deep neural networks. It was found that if you have more than 20 layers, it becomes almost impossible to train a neural network. You say, well, don't have 20 layers. Why do they have 20 layers? Because it works better if I can do it, or 40, right? So when the network is so deep, it cannot be trained. The training accuracy and generalization, both of them degrade. In fact, there is an analysis that says that the gradients actually start resembling white noise. If you want, I can explain what that means. So residual networks introduce what is called identity shortcut. Something like this should be of interest to people in neuroscience, to see if we have any analogies like that in the biological work. And after introducing these residual networks, we can use hundreds of layers. 200-layer neural network can be optimized, and the widening is corrected. So the person who came up with this idea of residual networks is Kai-Ming He. And he says that he came up with the idea using the following thought experiment. So the thought experiment is as following. Suppose that you have a neural network. This was a smaller neural network. We call it a shallow neural network. Suppose it has 20 layers only. And you train it. Now, suppose that after the neural network is trained, you put identity blocks in between. You stretch it and put an identity matrix in between. Well, you haven't changed it, right? You just made it deeper. So it's not going to be worse in terms of accuracy to have this bigger neural network. But if I try to train a neural network of this size, which I did not know it was good, it was okay to put identity here, I can't do it. So I don't get this. I cannot obtain this result by training that neural network before these ideas of residuals came, because a neural network is there's 0 probability that's going to say all those weights made them identity, right? It's going to do something to them. And so he says, why don't you allow for the possibility of identity mappings all the time in neural networks? So if a layer is not needed, maybe we can skip it. Insert identity mappings as an option. Here we know it's an identity mapping. So how can you insert an identity mapping as an option? This is your neural network, and here are 2 layers. Every 2 layers, put another arc, which is the identity arc. And this has a weight. Could be 0 or could be 1. And these have weights, but these weights could be 0, in which case you do the identity block. So what you do is you put these skip connections every 2 layers of the neural network. And in fact, if what you wanted to train, the other thing that he was saying is, if I want to train the identity function with a deep neural network, is an enormous cost, and I probably want to fail. And why should that be, right? Now, if I train a residual network on the identity function, and I started reasonably, I want to be able to do that, right? So this thing has done a huge difference. Has made a huge difference. Does anything like this exist in the human brain, in any animal brain? Or does any of that reasoning apply to that? Well, I mean, I don't know, the neuroscientists is talking about training our neural network or so on, but I've always found this idea interesting. So this is what you do. You have a prediction function plus the identity matrix every layer. The pictures that I showed you are precisely that. So this is now a neural network with 20 layers and with 110 layers with skip connections and without skip connections. And this was not done by the author of residual networks. It was done by someone else. And these are 2-dimensional slices. And are they real or not? I don't know, but they're enticing. They're kind of interesting. And they go together with this idea that you couldn't train without residual connections. Now, residual connections are so important that when you look at transformers, today transformers, there are residual elements between blocks too. That idea has sort of propagated into that. So among the thousand papers that have been written about training neural networks and heuristics and tricks, some of the few ideas that really remain are residual blocks and normalization. And is there a more intelligent way of doing normalization? What exactly does normalization do? There are actually, by the way, quite a few papers saying normalization improves things because of that. There are mathematical papers. And almost everywhere there's something unsatisfactory. There is some assumption. And residual neural networks make the landscape benign, softer. And in the proof, you see something that is not quite there, right? Maybe can only be done for a shallow neural network or something. So we have tons of ideas that have been proposed, a few that survive, and some that we're missing. I'll skip this thing about shattering of gradients. Something else maybe for a neuroscientist. If you just look at the Fs, that's a neural network. And what I mean by F is some layers. Neural network, some layers organized in that manner. And suppose that I have skip connections. I've added skip connections. Then what happens is that I can visualize this network as being a broader network. Because according to how I choose the coefficients, if I choose them 0 or 1, I could follow this path and not use the skip connections at all. Or I could use 1 and so on. So what we can see is that there are 2 to the n implicit paths that I'm really creating by putting a residual network. And adding just a block doubles the number of paths. And here's something that people have found out. If you take a neural network, in general, if you take a neural network for vision and you truncate weights, the whole thing goes to pieces. The results go to pieces. But if you go to a residual network and remove some of the elements after training at inference, so you have a neural network, a residual neural network, has been trained, everything is weights. And then you go on and make zeros. Some of the weights make them 0 arbitrarily. You still get good results. Because there are all these paths that are there. And there's theory about this. Aurora at Princeton. So here's a picture. VGG is a neural network for vision. If you remove elements, then the error becomes very large. You can never do anything. And this is the number where in the neural network you drop weights. at the beginning or at the end. And with a residual network, you have those things, and these spikes are of interest, but it doesn't matter. So the second question that I would talk to a neuroscientist is that with residual networks, I have a more healthy and more robust network. That's another interpretation of the many that there are about residual blocks. Are there such things in the human brain? And this is what you don't want to hear about, all this talk about optimization algorithms. I think all I want to put, one of the few things I wanted to make this discussion pretty general is this. Neural networks are trained with a variance of the stochastic gradient method. What is a stochastic gradient method? Well, you could take the whole gradient of the objective function and go downhill. But the objective function has 1 million terms. It's a regression, right? So you just sample a few of those as if you're only doing, and compute the gradient just with respect to those weights. And you do the reverse mode of automatic differentiation. You have your neural network. You do one pass, and in the backward pass, you compute the derivative. In general, there are 1 million functions. You do that for a batch of 600 or so on. So you don't get the true gradient, you get an approximation to the gradient, and it's stochastic because you choose them in a random way, not in a prescribed way, right? So you choose an approximation to the gradient, you move. How far do you move? There's this question about nonlinearity versus noise. If a function is smooth, you can move a lot. If the function changes very rapidly, you have to cut down. So you have to compensate those two with the step length, right? So everything starts with the stochastic gradient method, which, by the way, was invented by Robinson Monroe in 1951 and lay there dead for years and years. And how did the people in the community of machine learning discover the Robinson? How did they go and learn? I mean, Robinson, a very famous mathematician, right? Did all sorts of things. How did they find that he invented that method? Well, the way it happens a lot with it, they discover it, and they later realize that's the stochastic gradient method. If you start with a perceptron, Rosenblatt saying, okay, here's my perceptron, which is a 2-layer neural network. I make a guess and it's wrong. Oh, why don't you move a little bit this way? Why don't you move the little weight that way, right? And then how much? Well, by sensitivities and so on. Before you realize that you're doing something like this, and you want to do it at random. So they invented that back propagation, and people realized it's Robinson Monroe, for which there is a beautiful theory, part of it I described. But so the field of optimization for neural networks was static for many years, not many advances. But that is changing. So we wrote a paper in 2018 with Leon Botou and Frank Curtis. And in that paper, we have this picture that we thought is a roadmap for research and advancing algorithms for training neural networks. You have the stochastic gradient method is like the beginning. It's like Adam and Eve. Everything starts here. And there are two possibilities. One of them is to decrease the noise, make the gradient more and more exact, right? So you can always do that, and you can do a dynamically sampling algorithm. An algorithm that starts with a very inexact gradient, and as it progresses, it makes it more and more exact. Makes sense. Is that being used in practice? No. Why? Because it doesn't map well with the GPU. You can't be changing things like this. Otherwise, it would be used. But we're stuck with these realities, right? It would be good to do a dynamic sampling method, but it's not being done, and everything is being driven by things like, you know, what GPU do I have? And that's going to be determine the batch size. But now when we look at algorithms, what you can do is you shouldn't just be using the stochastic gradient method. The gradient has many components. You have 1 million variables, 1 million components. The magnitudes of these quantities are not for real, right? So doing a diagonal scaling is going to be imperative. In fact, this is what Adam does in Adagrad. At least there has to be a diagonal that scales those gradients, and they do it with historical information. They observe what the optimization has done and scales it that way. Now, we have ideas of quasi-Newton, but especially Gauss-Newton. When we have regression problems, Gauss-Newton methods are usually the way to do. You don't work with a Hessian, you work with a Gauss-Newton matrix. Because a Gauss-Newton matrix is always symmetric and positive definite. It only requires first derivatives. And the second derivative of a neural network maybe has curvature that is not interesting. So Gauss-Newton is an important thing. Trying to do variants of Newton and the natural gradient method are good. And I will finish here by saying we wrote that paper in 2018 saying, well, this is the way things could go. And to some extent, this is what's happening now with development in industry, except that we missed one big thing. There is one thing we didn't think about here, and therefore our paper should have only gotten a B- at best. Can anybody guess what I missed? What we missed? We missed. Adaptive gradient. Yeah, that I put in this category here. Diagonal scaling, what that changes over time. Yeah. Nonlinear conjugate gradient. Quasi-Newton is better than that. BFGS is better than nonlinear conjugate gradient. And conjugate gradient has history, so momentum is more like smoothing. Actually, I don't have it. I don't have the answer. Oh, yeah, here. Structure. All these methods are designed for general purpose optimization. And the software, for instance, that we have that is used, the virtue is that it's general purpose. So we see with great gratification that our software is being used everywhere, psychology, blah, 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 right, for any function. But a neural network is not any function. It's a composition, and for instance, it has layers. So one of the simpler ideas is you have the variables in the problem. How about if you update each layer separately? And it's like a coordinate descent method, where some variables are changed first. Well, that's too simple. The other thing is you want to approximate somehow the Gauss-Newton or covariance matrix or anything like that. They're enormous. But if they can be represented as Kronecker product, then you can have a much smaller representation of a big matrix with a Kronecker product. And that's what we forgot in here. It's a third dimension that is exploiting structure. And the structure that exists there is one that can be exploited with Kronecker products and maybe other things too. And this is right now actually where the action is. I mentioned that one of my students won that competition with a variant of what's called shampoo. You know, you have to forgive people in deep learning. They always come up with these names, right? The inception network, they're very good, right? The only really bad word is GPT, right? Why isn't it called crystal or magic? You know, it's called GPT. And what's it? Chat GPT, right? So there they missed it. But otherwise, shampoo, right? So there is a method that has a matrix in front, tries to be something like a Newton-like, uses Kronecker products, but still has to be implemented in a distributed system where a whole team worked for 2 years just to implement it. And it's way too complicated. But I think now we're converging because they feel like they have to simplify this. And we think also we have to simplify that. And I can give you here my secret ideas about what we're going to be doing in terms of simplifying the optimization. The first has to do with one of the things I mentioned at the very beginning. If you have 1 billion parameters, what is the dimension of the space you move in when you optimize? So subspace methods. And they're moving in that direction. How do you choose the subspace? At random? No. Through information of the problem. What information of the problem is there? If you look at the gradient of each layer and organize it as a matrix, has low rank. Pretty sure. You can use that information to decide on subspaces. The other thing is you can use this shampoo, which is an extension of these adaptive methods, and extract subspace information by doing approximate SVD or power method in there. And then you need preconditioners, but you need implicit preconditioners, nothing that involves a direct solve, but something like SSOR preconditioning, where you use an iterative method on some systems. So you have subspace, and in that subspace, you do some preconditioning. So now we have the iterative algorithm, and inside of that, there's a subspace where there's another iterative algorithm. And now the question is to get the balance of all those operations correctly. But some of the experiments show that you can do fine tuning and decrease the memory size enormously by doing subspace minimization. And I think that doing neural network for the masses is really important. And try to make it accessible for the masses. Thank you. I'll finish there. She said, I don't have a question. Yes.
Like to train neural network with not so much data, just kind of in context to get past it. Is there anything you can do with like optimization or anything you see the designs that allows you to do that with limited data to get a better result?
So the question is that in some contexts, you don't have enough data, as opposed to all what I discussed here, where you have tons of data. Is there something that you can do in order to train things this way? No, and in fact, I wonder if you should be using a neural network. Have you tried using random forests or other?
It's like structured networks where you define exactly how the numbers interact. They don't know about it.
Okay. I'm not sure if a neural network is the most conducive in that setting. But we don't know, right? So we don't know if we got to the Indies or we are in. There is somehow this feeling that artificial neural networks are probably like human neural networks, that you have to give it, several passes over the data. Even kids who learn words, but they have to be exposed to those words, right? I don't know if it's a vague idea, but I would try random forests.
So my question is about the comment about SGD and the SGD and the learning rate, how there's this sort of competing factor between the gradient descent and the variance. I wonder if there is in some context in which it's actually good to have the noise and the variance, for example, to escape saddle points and so on. And is this something that, like, I guess this is sort of orthogonal to a lot of the things we're talking about in terms of architecture. But if you imagine, like, if you have enough data, you don't have to do SGD, like one batch, everything. Do you think this is better?
Yeah, the question is, in SGD, you have a trade-off between noise and decreasing the objective function, and you want to suppress it. Couldn't it be good to actually use noise as a regularizer, maybe, to get you to the right solutions, right? And I believe so. I believe so, but that's the part of the picture where I had the picture of the white minimizer and the sharp minimizer that became controversial, because in our paper, we said, if you allow noise, a significant amount of noise, you're going to get to the white minimizer. And people have not agreed with that, right? So to what degree is noise useful? I think it is. And neural networks, you can work with neural networks that are not that big, so you can start decreasing the noise. We never got good generalization results by suppressing the noise too much. This is some years ago. And I'm going to look up, if you send me an email, I'll look up a paper, maybe the most recent paper that has looked at those issues. There's a lot of talk about this implicit regularization. And where is some good mathematical theory other than hunches and so on, right? It's been problematic. It's been difficult. People say, if you have a linear regression problem that doesn't have a unique solution, what do you want to find? Well, the minimum norm solution, right? What methods will get there? SGD will get there, other methods will not, right? But it's not linear regression. So once it's not there, you cannot prove it. And it's not satisfying to say that because it worked for linear regression. And Dave, you had something?
Whether the order in which the data is presented to the network, what role that plays in terms of improving order planning.
A big deal. This thing about processing data is something that usually doesn't get published. You don't know whether it's being done. Traditionally, there's something that was called curriculum learning that Benja used to propose a long time ago, saying, give the easiest examples first, and then the hardest examples. And I think that idea was abandoned some time ago. I do not know what is being done. Processing the data is so important, cleaning the data and so on. I have another one of my former students is a co-author of GPT-4, and he works on that, cleaning data, selecting data, using data, and I never get any information from him. So that's more or less my answer about data. They want to talk to me about optimization, and that's it. Now, one point about data, talking to Leon Botou, and I know Jan LeCun has the same idea, is that people talk a lot about fairness, and that there's a separate field, fairness and so on. And some of us are very skeptical about this. How can be a field called fairness? In economics, you have social welfare, but there's no field in economics called social welfare because it's application specific. If you have tax policy, then you try to decide what's a fair tax policy. And there you're going to spend all day and not agreeing, right? But you come up with one solution. And then you do something else. Broadband, opening broadband, and how do you charge, and who gets social welfare too? What is good for society, right? Is context-based. And Microsoft and I think Meta, both of them closed their fairness groups and merged them with a core group. Because some of us feel that bias is bias. I mean, if you catalog people incorrectly and say that I'm a monkey, I get upset. But if you get bacteria and they don't get upset, right? But it's in some sense the same thing. And so with respect to data, Jan LeCun and Leon Botou feel that most of what they have seen about unfairness can be solved by going and just improving the data. But I know I know many people will not agree with me because the whole conference is about fairness.
Privacy, are those separate?
Those are separate. Algorithmic, people talk about algorithmic fairness very seriously. And what do they mean? That people buy a program in order to hire employees, right? And you look at some characteristics, from that you make inference. And it has these errors, right? And people get upset, discriminate against someone, right? That's what they mean. Oh, and we're going to be using AI more and more for automatic decisions like that. How do we make sure that we don't have, we're making things worse, and making the world maybe more efficient, but more unfair, right? Because human intervention has been, our common senses go away from there, right?
Regulations, exactly.
And they're trying to put government regulation. I mean, I was looking at LLM in a company, and they told me, we're going to show you some results, but by the way, we haven't done all this cleaning that there is to do, putting rules saying you cannot say this, there's some things just hard-coded, right? So I started looking at the output, like ChatGPT output, and it's completely full of four-letter words. And I think it's some people like this, the way they write. But so, I mean, some things you can sort of prescribe. But what about the case of the Black Nazi? You read about this, right? Generative AI from Google, when they released Gemini, they could create images. You can say, create an image of a carpenter working inside the Hancock building, right? Who knows? Try to do a good thing. But if you say carpenter, you shouldn't assume that all the carpenters are men. So someone starts saying that, among professions, let's not start trying to reproduce all biases. Every category has to, And so someone writes there, create a picture of a Nazi, and there comes a black Nazi, because you wanted to be fair among all categories, right? So by being fair, now you worse, right? And if you put rules on the side, not in the system, it reminds us of our old AI, expert systems, and knowledge-based engineering. Talk to people, you find lots of rules, and with that, you will create a good architect or something like that, right? You create so many rules and they clash against each other, they're not enough, and so on and so forth. So putting fairness rules outside of the system, which academics would do, saying, oh, this has to be uniform among this group or whatever, right? Why that group, right? Why black Nazis doesn't go together, right? So if you try to impose that, it's going to be a problem. So, I mean, I don't know what you think, but if you say, create a picture of an electrician, something like that, and a man comes out, that's sort of the right thing, right? And I've met very few female electricians, right? So that, how do you factor that in? Are you going to put it all there, or are you just going to use the machine learning philosophy, which is just take all the data in the world and see what happens when you get an electrician, right? Instead of you trying to impose those rules. We got a little bit off topic, but it's important because many faculty members say they want to work on fairness in many different areas. And if it's true that it's not really an intellectually sound concept, then maybe you can save. I mean, it sounds good, but maybe we can save some work. Now, it's a little bit scary saying that, the machine learning approach is just put more data. And yeah, LLMs have an expert that gives examples, 200,000 examples are given to the system about this is the way you ask questions and so on. But it's very little compared to the bulk. But the bulk is just take all the information that is out there, and it's been working with some rules, so like your vocabulary is.
I have the impression from the way you're going through this that machine learning developed initially for classification problems, and now it's trying to do prediction. And do you think, which seems to me like very different? I don't think those is the same.
She's saying, I believe that machine learning was developed initially for classification, and now it's being used for prediction. That's the first part of your question, right? Yeah, no, I don't think so. I think
it started with prediction. I was wondering if it would commute, like we get to the same. It's a philosophical.
I think it was always prediction. Oh, it's always prediction. It's a way of thinking that we applied mathematicians were not used to do. And it started with Google, for instance, the Google search engine. When you do a query, it doesn't tell you what the result is. It gives you 1,000 examples with certain probability, right? So it's predicting. Now it's gone beyond. So we do image recognition. What you do is the neural network, the last layer may have 10,000 nodes corresponding to 10,000 classes. Is this a car, blah, 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 right? And it gives you the probability of each one of them. It's always been a prediction system. Now, large language models are a prediction of what the next word is. That's what it does. And if you let it going, it says it keeps predicting, but it's still prediction. It's probabilities and so on. And I mean, I was an optimizer. People press a button. Here's how you design a wing of an airplane, right? And it doesn't give you all these possibilities. I think it's pretty interesting. Since you work on climate models, I spent 10 years working on the weather forecasting system for DVAR. I mean, it's not known because I only wrote one paper, For 10 years with ECMWF, we were working on 4D-VAR, which requires optimization in the loop, very similar to this, backpropagation and so on. And I came with my mindset of deterministic optimization. You know, you have a Navier-Stokes equation, you want to find out what the initial conditions are, you do the forecast and you get the predictions, right? And then, you know, the more I saw about this, they're spending more and more money defining the covariance matrices in the objective function. This is a statistics problem, right? The interaction between variables and so on. So now I have this weather prediction system and I have machine learning prediction systems, and they have so many similarities. Large scale, there's uncertainty, blah, blah, blah. Derivatives, it works in the world of real numbers and so on. And the only difference is that one of them is an embedded physical model in Navier-Stokes equations. The other one has a bunch of neurons, right? A collection of neurons and no understanding of computer vision. But structurally, mathematically, there are many similarities in these two prediction systems, right? And also, when you get a forecast, there's not one, there's a whole bunch of prediction systems. ECMWF will do like 10, and then people will select something. And with hurricanes, it's one of the few places where people are given results like that. Many people, statisticians say, why aren't we doing this all the time? Only for hurricanes, they tell you, it may be here or here's the level of uncertainty. And on other things in everyday life where we know there's uncertainty, we do not display that. And we don't make that effort of displaying it, right? So if someone asks me to solve an optimization problem, and I know that the data is not completely well known, then I should say, well, give me the distribution of some of the things that are pretty unknown, and let's find a set of solutions.
I'm certainly not an expert, but if I look at like the connectomes that are coming out, you know, people that are trying to actually look at what brains look like, seems like there's a lot more connections that are more like the skips. You know, just sort of random things that jump across. There certainly are layers, but and that's sort of the main structure, but there's a lot more of the other types.
So the question is, why are we looking at more and more layers? In the brain, there are more things like skip connections. I would just say because it works for them, right? Are there good works on similarities between artificial neural networks and real neural networks?
There's just a bunch of papers showing that why
But so these questions like skip connections, they exist in the brain. Mary, when you ask about what does it do classification or predictions, when people say, why do neural networks work well? If you talk to like the founders of the current field, they will say they're very good at learning representations. So that's what they do. You get an image based on pixels. You're not going to make predictions based on pixels. Are you going to make a prediction based on mouths and contours and shapes? And yes, those are better representation, right? And every layer of the neural network is creating a different representation. And the last one, if you started at the last one, it says, here's the data. That's the way you should represent it, like the basis in which you should represent it, and now do a prediction, right? And so having lots of layers, do you really need lots of layers in order to get that representation correct, right? I mean, our common sense is, why would you need 200, right? But I have no idea. Yeah. Are we still online or? Oh, I'm still here. Okay, so the question is that I talked about removing connections when you have a skip connection architecture, that if you remove some arcs, some weights, you still get predictions. Do you have any intuition about why that works? No, other than the one I said that there are many paths and you've created a much more powerful network. Other than that, I would not know what to say. And I can give you a paper, again, one of those that does nice math and not complete story. But again, it starts counting the probability that each one of them will have the right. Well, I can show you. I can show you that paper. No, I don't have intuition.